It is my pleasure to present our latest work, Compact and Foldable Hip Exoskeleton with High Torque Density Actuator for walking and stair climbing assistance in young and elderly adults. Exoskeletons have shown potential in aiding human movements. However, current state-of-the-art exoskeletons are still designed to be used in controlled environments such as clinics and laboratories. The first issue is that most research groups use either off-the-shelf conventional high-speed motors with large gear ratios or off-the-shelf quasi-direct drive actuators, also known as QDD actuators. However, there is limited literature to reveal the underlying design guidelines of an ideal QDD actuator tailored for exoskeleton use. The second issue is that current state-of-the-art exoskeletons use rigid frames that does not accurately conform to the user's body and thus making them uncomfortable and limiting the perceived assistance force. We noticed this trend after reviewing the specifications of the state-of-the-art exoskeletons. As you can see, our newly designed hip exoskeleton is the most compact with the highest torque density. Our vision is to bring exoskeletons out of laboratory settings and into community settings, allowing them to be used as personal mobility devices for everyone and everywhere. To do this, the exoskeleton needs to be lighter, with a lower profile that makes it easier to wear in more environments in time. The actuator is a critical component of exoskeletons, and it needs to produce high torque density, yet small in size to be unobtrusive when worn by the wearer. Our high torque density actuator is composed of an 18 stator teeth and 20 roller pole permanent magnet synchronous motor and a low ratio transmission, drive board, magnetic encoder, bearings, and housing. Here's the assembled stator with a wound fractional slot concentrated winding and assembled outer rotor with a surface-mounted permanent magnet. For the second challenge, we designed our hip exoskeleton to be flexible, which allowed the frame and wearables to hug the user's natural body curvature without being too tight, making it comfortable for a wider range of body types. Compared to our previous rigid design, this design makes the exoskeleton much easier to wear and more comfortable to wear. We also considered the exoskeleton during operation and designed the self-aligning mechanism for the thigh brace. The self-aligning mechanism of the thigh brace allowed the anchor point on the thigh to move with the user and thus preventing the exoskeleton from shifting when in operation. Validating our work, we first conducted benchtop experiments to validate our high torque density actuator. The actuator has shown greater torque density with an increase of 28% and 74% compared to similar actuators from T-Motor and my actuator, respectively. Paired with off-the-shelf high-speed motors with large gear ratios and off-the-shelf QDD actuators, our actuator delivered the highest torque density and package factor with the lowest weight and smallest size. Compared to our previous exoskeleton, our new design allowed for better accessibility due to its low profile, making it easier to steer in multiple spaces, such as sitting in tight chairs and getting in and out of cars. To demonstrate the capability of our exoskeleton, we conducted a preliminary metabolic test for human subjects. We recruited 9 healthy subjects, where 6 were young adults and 3 are elderly adults. The first test involved all 9 recruited healthy subjects where they walked for 6 minutes at 1.25 meters per second, wearing the exoskeletons, providing assistance using the Samsung controller as a benchmark of the state-of-the-art hip exoskeletons. Then they were asked to walk yet again, used without wearing the exoskeletons and measure the net metabolic cost. Here are the experimental results for our walking metabolic test. The young subjects had a net metabolic cost reduction of 13.75%, and the elderly subjects had a reduction of 8.74%. The reason why the younger adults had a greater reduction was due to the fact that 3 of them were experienced users of exoskeletons. And previous studies have shown that the more experienced a user is with an exoskeleton, the greater effect it has on their net metabolic cost reduction. Next, we conducted a metabolic test for stair-climbing with the 6 young adults for 6 minutes to validate how the exoskeleton will function for a different activity. The experimental results show that our exoskeleton decreased the net metabolic cost by 9.11% during stair-climbing. Lastly, each subject filled a system usability scale survey, where we can see that most subjects thought that the exoskeleton was easy to wear and to use. We scored a 78 out of 100 compared to the 68 out of 100 in the literature. Our work shows significant progress in bringing assistive devices like exoskeletons out of labs and into the community to help individuals in everyday life.